Diffraction. Diffraction. First let us try to understand what is meant by diffraction. For this purpose, let us take a source S and a slit, a small pinhole, a slit with small pinhole, and let us take a screen. Place the screen at some distance. According to rectilinear propagation, the light should illuminate the region between PQ. The region between PQ should be illuminated according to rectilinear propagation, and the region beyond P and beyond Q should be geometrical shadow region. It should be shadow region. But if we carefully observe, a small amount of light enters this region, geometrical shadow region, and beyond P up to small distance, nearby P, we notice a small amount of light. Similarly, beyond Q also we notice small amount of illumination in the geometrical shadow. Let us consider another case. Here S is source and the short line indicates a small obstacle. A small body is placed in the path of light. Then, according to rectilinear propagation, the geometrical shadow of this linear object should be from P to Q. The PQ region should consist of geometrical shadow region. Beyond P and beyond Q, it is illuminated region. When we carefully observe the shadow region, the edges of the shadow region near to P and near to Q, we notice a small amount of illumination of light. From these two examples, what we notice is the light is entering into the geometrical shadow region, near the shadow edges. Near the edges of the shadow region, the light is entering. But it is not possible, according to rectilinear propagation of light, this illumination is not possible in the shadow region. Diffraction phenomenon. Bending of light at small obstacles or at straight edges is called diffraction. Bending of light at small obstacles or at straight edges is called diffraction. We can also define diffraction as the encroachment of light into the geometrical shadow. The encroachment of light into the geometrical shadow is called diffraction. These two phenomena we have noticed. Bending is noticed if light is allowed to pass through narrow holes or an obstacle is placed in its path. We notice bending of light rays when light is allowed to pass through a narrow hole, or if an obstacle is placed in its path, or if small edge like the edge of a blade is placed, sharp edge is placed in the path of light. And this bending is very small if the size of the object is large compared to the wavelength of light used. Bending is very small if the size of the obstacle is large compared to the wavelength of the light used. But bending will be appreciable when the size of the obstacle is that of the wavelength of light used. Bending is appreciable when the size of the obstacle is that of the wavelength of light used. The condition for observing diffraction at an obstacle is L is equal to b square by 4 lambda. L is equal to b square by 4 lambda, where L is the distance of the screen from the obstacle. B is size of the object. Lambda, the wavelength of light used. To understand diffraction, we need to understand Fresnel's half-period zones. Fresnel has explained diffraction with the concept of half-period zones. First, let us try to understand what is meant by half-period zones. S is a source of monochromatic light. S is a source of monochromatic light of wavelength lambda. From S, the light is moving to the right. Let us consider the wavefront passing through the point O. The curve, the arc, represents the wavefront at some instant. Let us consider a point P in front of the wavefront at a distance b from the wavefront. P is a point at a distance b from the wavefront. When we join SP, if it meets the wavefront at O, then O is called the pole of the wavefront. Pole of the point P on the wavefront. Pole of the point P on the wavefront. Now, take an arc of length b plus lambda by 2, and take P as the center. Draw an arc with b plus lambda by 2 as radius, such that this arc is drawn on the surface of the wavefront. In fact, a circle will be formed on the wavefront. A circle will be drawn on the wavefront with a radius b plus lambda by 2 with P as center. That means we have to sweep a cone with b plus lambda by 2 as the radius vector. The tip of this radius vector, it describes a circle on the wavefront. Next, take another radius of length b plus 2 lambda by 2. Take P as pole and once again draw another circle on the wavefront. Like this, draw different circles on the wavefront with P as center and b plus 3 lambda by 2 as one radius vector, b plus 4 lambda by 2, b plus 5 lambda by 2, etc. Like this, we construct circles on the surface of the wavefront. Then, the area of the first circle. The area of the first circle is called 0th half-period zone. The area of the first circle is 0th half-period zone. Then, the area in between the second circle and the first circle. The area between the first circle and the second circle gives the first half-period zone. The area between the second circle and third circle gives second half-period zone. The area between the third circle and fourth circle gives the third half-period zone. Like this, the wavefront is imagined to be composed of different areas, different zones known as half-period zones. 0th half-period zone, first half-period zone, second half-period zone, third half-period zone, etc. These are the half-period zones with respect to the point P, and O is the pole of the wavefront with respect to. Another form of Fresnel's half-period zones. Another way of representing Fresnel's half-period zones. Let us take a plane wavefront. In the previous case, we have taken a spherical wavefront. Now let us take a plane wavefront. The square on the screen represents, a colored screen represents, colored square represents the wavefront. Then P is a point in front of the wavefront at a distance b. P is in front of the screen at some distance b. And PO is the perpendicular drawn onto the wavefront. O is the pole of the wavefront. O is called the pole. Then Take a radius vector of length b plus lambda by 2 and p as center. Sweep a cone, then it describes the circle with radius r0. Take a radius vector of length b plus 2 lambda by 2 and p as center and sweep an arc, sweep a cone with the radius vector. Then the tip of this radius vector describes the circle with radius r1. Similarly, the tip of the radius vector with radius b plus 3 lambda by 2, it sweeps the circle of radius r2. Like this, different circles will be drawn. Like this, different circles are drawn on the surface of this wavefront. On the surface of the wavefront. Then, the area of the first circle with r0 as radius. The area of the circle with r0 as radius is 0th half period zone. 0th half period zone. The area between the circles with radii r0 and r1. The area in between the circles of radii r1 and r0 is first half period zone. The area between the concentric circles with radii r2 and r1 is second half period zone. Like this, we divide the wavefront into number of half period zones. Number of half period zones. And O is pole of the wavefront. O is pole of the wavefront. Around this point, pole, we notice half period zones. Fresnel has explained diffraction. Explanation of diffraction is done by Fresnel. Actually, Fresnel used Huygens wave principle. Fresnel used Huygens wave principle and the concept of half period zones introduced by him in explaining diffraction. So he combined his concept of half period zones with Huygens wave principle and explained diffraction. This can be named as Huygens-Fresnel principle. This can be named as Huygens-Fresnel principle. According to Huygens, each point on the wavefront acts as a source of secondary wavelets, and these secondary wavelets travel in the forward direction only. Each point on the wavefront acts as a source of secondary wavelets, and they travel in the forward direction only. These secondary wavelets are mutually coherent. That is, they have constant phase difference. They will have constant phase difference. So they are taken as coherent wavelets. Fresnel imagined a small region on the wavefront. Fresnel imagined a small region on the wavefront which is incident on the straight edge and divided it into half period zones. The interference of the secondary wavelets from the half period zones will produce diffraction fringes. Diffraction fringes will be produced. Like the bands produced in interference, fringes will be produced because of the interference of the superimposition of secondary wavelets coming from these half period zones. Like this, he explained the diffraction fringes. Huygens-Fresnel principle. Huygens-Fresnel principle. Let us consider a primary wavefront S. On the primary wavefront S, let us take a small elemental area ds. ds is an elemental area on the primary wavefront S. N is the unit normal to this elemental area ds. N is unit normal to the elemental area ds. Consider any point P at a distance r from the elemental wavefront ds. From the elemental area ds, consider a point P at a distance r. The angle between the direction of unit vector n, the angle between the direction of unit vector n and the distance direction of OP is theta. Theta is the angle between the distance direction and the normal unit vector normal to the elemental area. The intensity at point P depends on the distance r of point P from the elemental wavefront ds, the distance r of point P from the elemental wavefront ds, the angle theta between the normal and the distance r, the angle between the normal and the distance r, that is theta, the effective intensity at P. The effective intensity at P is the sum of the intensities produced. The resultant intensity, that is the sum of the intensities produced by different elementary regions, that is half period zones, into which the primary wavefront is divided. This ds elemental wavefront will be divided. Now this entire wavefront, yes, is divided into elemental wavefronts like ds, and the intensity at P is the result of all the intensities produced due to different parts of this wavefront. Like this, the intensity at a point is defined, it is indicated, it is explained by Huygens principle. Intensity at a point P due to the wavelets, due to the energy coming from the secondary wavelets. Intensity at a point P due to the wavefront. We know that the intensity is proportional to the square of the amplitude. We know that the intensity is proportional to the square of the amplitude. When we consider the zones, when we consider the Fresnel's half period zones, the wavelets coming from the half period zones, adjacent half period zones, will have a phase difference pi. The significance of half period zones is the phase difference of the waves coming from adjacent zones is pi. The amplitude produced by the waves are dependent on the phase difference. The amplitudes produced by the waves are dependent on the phase difference. If the amplitude is positive by the wavelets coming from one half period zone, if the amplitude created is positive by the wavelets coming from one half period zone, then the amplitude will be negative for the waves coming from the neighboring half period zone. The amplitude created by the secondary wavelets coming from one zone, if it is positive, the amplitude created by the wavelets coming from the adjacent zone, neighboring zone, will be negative. So alternate zones will have positive, negative amplitudes. Let A1, A2, A3, A4, etc. Let A1, A2, A3, A4 dash 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 are the amplitudes produced by the secondary wavelets coming from different zones. Then the resultant amplitude at P will be A is equal to A1 minus A2 plus A3 minus A4 plus A5. Like this we have to add the amplitudes. A1 is positive, A2 is negative, A3 is positive, A4 is negative. So the resultant amplitude A is equal to A1 minus A2 plus A3 minus A4 plus dash dash dash. The amplitudes are approximately equal, nearly equal, but not exactly equal. So the intensity produced by, most of the intensity produced by one zone will be nullified by the adjacent zone. Because the amplitudes are in opposite direction, the resultant intensity will be almost zero if two adjacent zones produce intensity at point P. The intensity produced at point P by two adjacent zones is nearly zero because the amplitudes are approximately equal. If only the first two half period zones are allowed, if only the first two half period zones are allowed and the remaining, the intensity of light coming from the remaining is cut off, then the point P is nearly dark. If we allow the light coming from 0th half period zone and first half period zone, then the point P becomes dark. If the first three are allowed and the remaining are cut off, then P will be bright. That is, if light is allowed from the 0th half period zone, first half period zone and second half period zone, then the point P will be bright. In general, if odd number of zones are allowed, the point P is bright. If odd number of zones are allowed, the point P is bright. And if even number of zones are allowed, the point P is dark. P is dark if even number of half period zones are allowed, and P is bright if odd number of half period zones are allowed. Diffraction at straight edge. Diffraction at straight edge. S is a monochromatic source of light, yellow source of light. SL represents a slit which allows a narrow beam of light. AB is a straight edge. It is placed such that the edge A touches the beam of light coming from the slit. The rays passing through the edge A strike the screen at point C. We place a screen at some distance from the edge. The rays passing through the edge A, they strike the screen at C. And then if we observe on the screen, above C we see a bright band, yellow band, followed by it a dark band, followed by it a bright band of less width, followed by a dark band of less width. Like this, we notice alternate bright and dark bands above C. Above C, we notice alternately bright and dark bands. The width of these bands will be decreasing continuously. Below C, in the geometrical shadow, we notice faint illumination, light illumination, whose intensity will be decreasing as we proceed deep into the shadow in the downward direction. As we move into the geometrical shadow in the downward direction, we notice decreasing faint illumination. So this is how the diffraction phenomenon appears due to a straight edge. This is what we observe, the diffraction phenomenon, when we use a straight edge like AB. Explanation of diffraction at straight edge. Explanation of diffraction at straight edge. To explain the diffraction, first we have to understand the following phenomena. So source is S, slit SL is slit, and a narrow beam is passing through the slit, and an obstacle is placed, and a screen is placed at some distance. We consider points P, C, Q on the screen. Now SC intersects the wavefront. The curve indicates the wavefront incident on the edge, straight edge. O is point on the wavefront. It is the point which is obtained by intersection of SC. So O becomes the pole of wavefront for point C. Similarly, SP is meeting the wavefront at another point. So that point becomes the pole of wavefront when we consider P. Take SQ. SQ is intersecting the wavefront at another point below O. So that point becomes the pole of wavefront for point Q. If we consider another point above P, the pole of the wavefront is moving in the upward direction. Like this, the pole of the wavefront is not constant, it depends on the point of observation on the screen. The pole of wavefront depends on the point of observation on the screen. Whenever we consider a wavefront, pole of the wavefront, we have to imagine Fresnel's half-period zones around that pole of wavefront. Fresnel's half-period zones will be situated around this point, that is the pole of wavefront. So when we consider point C, the half-period zones, they center around O. Around O they are situated. If we carefully observe, the obstacle, it obstructs half of the circles in the wavefront. Upper half of the circles of the half-period zones are exposed and lower half of the circles are cut off. So the upper half of the wavefront is completely exposed and the lower half of wavefront is cut off by the obstacle, a straight edge. Let us take the point P. When we consider the point P, the pole of the wavefront lies just above O. So the pole of the, around this pole of wavefront we have to imagine Fresnel's half-period zones. When we consider the pole for P, upper half of wavefront is exposed, that is allowed. When we consider the lower half of wavefront, a small number of half-period zones are situated above the straight edge and the pole of the wavefront for P. So a small number of half-period zones are exposed in the lower half of the wavefront. When we consider point P, we notice along with the upper half of wavefront, a small number of half-period zones are exposed in the lower half of wavefront. Consider point Q. For point Q, the pole of wavefront lies below O. So the lower half of wavefront, that is the circles, half circles, are all cut off. Along with these lower half of wavefront, a small number of half-period zones, in the upper half of the wavefront is also cut off. A small number of half-period zones in the upper half of wavefront are also cut off by the straight edge. Now we have to understand this before we understand the intensity on the screen. Fresnel diffraction above C. Explanation of diffraction phenomenon above C. The mathematical treatment is very complicated. The mathematical treatment for explanation is very complicated. Yet we can explain this phenomenon with the help of Fresnel's half-period zones. With the help of Fresnel's half-period zones, we can explain this phenomenon. In this class of diffraction, the distance of object and the screen are very small. Object and screen are very close. So there is no need of lenses for observing this class of diffraction. We can observe this diffraction phenomenon with our naked eye. Here, the wavefront is a spherical wavefront. You must have noticed that we have drawn a curve which represents a spherical wavefront. So a spherical wavefront, it is incident on the straight edge. For a point C just above, C, a small number of half-period zones in the lower half of wavefront are exposed. We have already studied that if we consider a point P just above C, for such a point, a small number of half-period zones are exposed in the lower half of the wavefront in addition to the entire upper half of wavefront. The intensity at that point depends on the number of such exposed half-period zones. The intensity at a point above C depends on the number of exposed half-period zones in the lower half of wavefront. If the exposed number is odd, the point will be bright. If the exposed number is even, the point is dark. We know the intensity due to one half-period zone is annulled, is nullified by the neighboring half-period zone. So, if the number of exposed half-period zones is odd, the point P will be bright. If the number of exposed half-period zones is even, the point will be dark. So, we notice bright and dark zones, periods, regions above C. The width of these bands will be decreasing continuously as we move up from C. As we move up from C, we notice the width of these bands will be decreasing continuously. Fresnel diffraction below C. Fresnel diffraction below C. According to rectilinear propagation of light, the region below C must be completely dark and it must be uniformly dark. The region below C must be completely and uniformly dark according to rectilinear propagation. But we notice a faint illumination below the geometrical edge. Below C, in the geometrical edge, we notice faint illumination. This illumination is due to the secondary wavelets coming from the half-period zones just near the pole of the wavefront. This illumination is due to the secondary wavelets coming from the half-period zones which are just near the pole of the wavefront. As we proceed into the geometrical shadow below C, as we move into the geometrical shadow, the illuminating number of half-period zones will be decreasing, because already half of the lower half of wavefront is cut off. As we move down, some of the half-period zones in the upper half of wavefront will also be cut off. Moreover, the obliquity will be increasing. As the obliquity increases, the intensity decreases. Hence, the intensity decreases because of the zones, cut off of the zones near the pole of wavefront, and because of the obliquity factor. Fraunhofer diffraction. Just now we have studied Fresnel half-period zones and Fresnel diffraction. There is another diffraction known as Fraunhofer diffraction. In Fraunhofer diffraction, we take a plane wavefront. If the wavefront is far off from the source, then we consider such a wavefront as plane wavefront. Here we take a plane wavefront, and a slit AB of width D is taken. A slit AB of width D is taken, and it is divided into number of small elemental strips of thickness dx. Small strips of thickness dx. This slit AB is divided into a large number of small elemental strips of thickness dx, and the rays the secondary wavelets, they will be incident on a lens which is an achromatic lens. L is an achromatic lens, and the diffraction takes place and we place a screen beyond this lens. On this screen we notice diffraction phenomena. So P is a point on the screen. Then the angle theta made by this wavefront, the wave radius, secondary wavelets with the axis of this phenomena, is known as angle of diffraction. Explanation of Fraunhofer diffraction. We know that we are using a plane wavefront. If the source is at a large distance, the wavefront becomes a plane wavefront. This plane wavefront is derived by using a convex lens. That means if the source is placed or slit is placed at the focus of a convex lens, then the emergent beam will be parallel beam, so that becomes a plane wavefront. This plane wavefront is imagined to be divided into a large number of strips, each of width dx. The plane wavefront is imagined to be divided into a large number of small strips, each of width dx. The secondary wavelets from these strips get superimposed at the point P on the screen. The secondary wavelets from these strips get superimposed at the point P on the screen. We know that the intensity is proportional to the square of the amplitude. Moreover, it depends on the obliquity factor theta. So the intensity at P depends on the angle theta, the diffraction angle, and the area of the strips. If C is length of each strip, we imagined already its thickness is dx, then C dx becomes the area of the strip. So the intensity depends on this value C dx, the length and the thickness. C dx is the area of the strip. So the intensity depends on this area, because the amplitude of the resultant wave, the amplitude of the wave depends on this area. Hence intensity depends on the area of the strip. Like this, once again the resultant intensity will be the sum. It will be obtained by using resultant amplitude. The resultant amplitude will be obtained by the sum of the amplitudes. Fraunhofer diffraction can be observed easily, or it is appreciable. It is applicable only when B squared by L is far less than lambda. Fraunhofer diffraction is applicable only if B squared by L is far less than lambda. Applicability of different phenomena. The applicability of different phenomena depends on the factor B squared by L lambda. The applicability of different phenomena depends on the factor B squared by L lambda. For Fraunhofer diffraction, this factor B squared by L lambda should be less than far less than 1. For applicability of Fresnel's diffraction, this B squared by L lambda should be equal to 1. For Fresnel diffraction, this factor should be equal to 1. For application of geometrical optics, this value B squared by L lambda should be far greater than 1. It should be far greater than 1 for geometrical optics, equal to 1 for Fresnel diffraction, and less than 1 for Fraunhofer diffraction. Application of diffraction. Where can we use this diffraction phenomenon? By using diffraction phenomenon, the wavelength of light, monochromatic light or composite light, can be estimated. We can determine the wavelength of light using diffraction phenomenon. Wavelength of X-rays can be estimated with the diffraction phenomenon. The structures of solids can be determined. The structures of solids can be determined by diffraction of X-rays, diffraction of electrons and neutrons. By the phenomenon of diffraction, we can estimate the structure of solids. Velocity of sound in liquids, organic and inorganic liquids, can be estimated by diffraction phenomenon. The size and shape of ulcers, tumors, etc. in human body can be located with diffraction phenomenon. The size and shape of ulcers and tumors can be estimated in human body by using this diffraction phenomenon.